Effect of process parameters on temperature of alloy. Abstract: in recent years cast alloys has been expanding widely in aeronautical, automobile and general industries. The wear characteristics of these alloys depend upon the material morphology such as composition, size, shape, and distribution of micro-constituents and service conditions such as load, contact surface, contact time and sliding speed. The influence of variables viz., contact time, sliding speed, and normal pressure on wear behavior were studied. With the increase of contact time, the corresponding frictional temperature rises steadily due to the increased conversion of frictional energy into heat energy and no influence of sliding speed on the temperature rise in the specimen. The temperature rise in all the specimens increases with increasing of normal pressure on the specimens. Keywords: tribology, ALSIMGFE alloy, temperature, sliding speed, normal pressure. 1. Introduction. Aluminium alloys are attractive alternatives to ferrous materials for tribological applications due to their low density and high thermal conductivity. However, their uses have been limited by their inferior strength, rigidity, and wear resistance. 1. The wear of components made of ALSIMGFE alloys depend on number of material-related parameters. The use of aluminium alloys in industry is increasing owing to their high strength/density ratios and other advantage properties. In particular, the effect of alloy composition on work hardening behavior has been investigated. This alloy showed the great initial hardness and the most surface hardening at all loads. The A3004, being the softest alloy, exhibited the most substantial reduction in specific wear rate with load, being the highest at 2,3 N of all alloys by some margin, but similar to the other materials at 140 N3. The commercially important alloys contain copper as major addition, and the phase reactions, which occur, are those between an aluminium solid solution and the intermetallic phases CuAl2 and CuMgAl2 4,5. A6061 alloy. Another commercial alloy has a few Cu. The best wear resistance of 6061 alloy could be attributed to the highest hardness and lowest coefficient of friction 6. In this study, evaluation of wear characteristics of ALSIMGFE alloys that was aged at different temperatures on pin-on-disc under dry sliding system. Material and experimental study. The lowing raw materials were used to evaluate the wear and machining characteristics ALSIMGFE alloy. Samples: ALSI alloy, pure magnesium, pure aluminum, pure iron, sand mold, investment shell, and cast iron mold, die. Fluxing agent, degasifier. The alloy was prepared and chemical analysis of their ingredients was done. The chemical composition of alloy is given in Table 1. The sand mold, investment shell, and cast iron mold were employed to prepare the samples for wear tests. The melts were degasified with tetrachloroethane tablets. And ALSIMGFE alloys were melted in an oil-fired furnace. The melting losses of aluminum and magnesium were taken into account while preparing the charge. During melting, the charge was fluxed with Coverall 11, a Fosco company product, to prevent dressing. The molten metal was then degasified by tetrachloroethane, in solid form, using a plunger ending in a small inverted crucible. The melt was also modified with sodium and refined with Al-Ti master alloy in the crucible before pouring. The crucibles were made of graphite. The dross-removed melt was finally gravity poured into the preheated sand mold, investment shell, and metal die. The cavity shape is cylindrical in all the methods of casting. The pin specimens were prepared from ALSIMGFE alloys. The dimensions of the specimens was 6 mm diameter and 20 mm length. A pin-on-disc type friction and wear monitor, ASTM-G99, was used to evaluate the wear behavior of ALSIMGFE alloys against hardened ground steel, EN32, disc having hardness of RC62 and surface roughness, RA, 0.6. Wear tests include the measurement of weight loss using electronic weighing balance with accuracy up to 0.1 mg, temperature of pin using thermocouple, and friction force with data acquisition system. The mechanical properties and metallurgical morphology were investigated to evaluate the wear behavior of these alloys. Temperature measurements of wear pin during the sliding were carried out with chromolalumyl thermocouple. Thermocouplets were placed into a hole of 2 mm diameter at 1.5 mm away from sliding surface. Temperature was recorded with the help of digital temperature indicator. Results and discussion. Mechanical properties. The mechanical properties of AlSiMgFe alloys are given in Table 2. The mechanical properties of die-cast alloy are superior to investment cast and sand alloys. The reason could be the fine grain structure in the die-cast alloys. The grain structure in the casting is influenced by the solidification process. Effect of contact time, sliding speed, and normal pressure on temperature. The influence of contact time on the temperature generated in the specimen is shown in Figure 3. The temperature rise in the specimen is proportional to its contact time with the abrasive disc during the wear test. With the increase of contact time, the corresponding frictional temperature rises steadily due to the increased conversion of frictional energy into heat energy. The influence of sliding speed on the temperature generated is illustrated in Figure 4. It is clearly observed there is no influence of sliding speed on the temperature rise in the specimen. It may be attributed to the slip phenomena, which creates new interface between the specimen and the abrasive disc continuously. Consequently, there may be interruption for the temperature flow into the specimen because the heat experienced interface is passed on by the new and cold interface. The mathematical relation between the sliding speed and the temperature rise is linear. The gradient of the curves is 0.1 only for all the specimens. The temperature rise due to change in sliding speed is negligible. The influence of normal pressure on the temperature rise of specimens is demonstrated in Figure 5. The temperature rise in all the specimens increases with increasing of normal pressure on the specimens. Moreover, the increase in the normal pressure on the specimen results the plastic deformation of the wearing surface and subsequently rise in frictional temperature. The temperature rise is exponential of normal pressure on the specimen. This may be on account of wear mechanism consisting of abrasive, adhesive, and melt wear phenomena. The microstructures of worn specimens are revealed in Figure 7. The grains become finer owing to the work hardening. The increase in hardness values of worn specimens indicates that the work hardening effect dominates the softening effect. The softening of structure in the wearing specimens aids in the diffusion across the change in hardness of the worn specimens is shown in Figure 6. It can be seen that the hardness values increase after wear test. The increase in hardness in the worn specimens may be attributed to the work, strain, hardening and the frictional temperature. Figure 7 shows temp photomicrographs of worn surfaces of AlSiMgFe alloy exhibiting different wear morphologies. It is clearly seen that the wear particles are detached from the severely deformed material. Figure 7a and 7b show that the formation of abrasive grooves and particle detachment. Figure 7c shows the absence of large grains in die-cast specimens. Conclusions. The following conclusions can be drawn from the test results. The temperature increases with increasing contact time at constant normal pressure and sliding speed. There is no influence of increasing sliding speed on the temperature rise in the specimen at constant normal pressure and contact time. The temperature rise in all specimens increases with increasing normal pressure at constant contact time and sliding speed.